Hi friends, in this class we will continue our discussion on orthogonal projections, and we will have a number of theorems we will define, and we will solve some problems based on those theorems. Now, okay, so the theorem, the first theorem will be this theorem number 8. All these theorems which I have, I'm going to define will have the proof, but the proof is not that much important in your exams. So if you get time, you go through that proof, or we will discuss that later. The proof. Okay. Now the theorem. This theorem says that theorem 8, that orthogonal decomposition theorem. This the continuation of the concepts that we have already discussed earlier classes. So in this here we are extending. In the previous class we have a subspace. We have defined a subspace. Subspace L we have named it, which is the line passing through the origin. Passing through the origin, and it is extending from minus infinity to plus infinity. So this is our subspace L, and this subspace L we have told that this subspace L is spanned by a vector U, span U, right? Like this. U will be like this, and yes, if you span this U, then you will get this straight line, which is the subspace L. So this L, I am replacing this L as W. So you can, it doesn't matter if you name it L, W, S, X, Y, Z. You can give any name to that subspace. So for the time being, I am calling it as W. Like in the previous class, I named it as L because it is a straight line. Now I am generalizing this into W. Okay, this is a subspace which is named as W. So this is W is a subspace that is a one-dimensional subspace. One-dimensional subspace. Right. Now, in the case of one-dimensional subspace, and if we have a vector y like this, then we have shown that this y can be written as y cap plus z, where this y cap will belongs to this one-dimensional subspace W, and the z will be normal or orthogonal to the W subspace or straight line. Or you can say that this z will belongs to W perpendicular. Okay, this symbol W perpendicular. Right. Okay. Yes. Now I'm extending this concept into dimension greater than 1. That means our subspace W is having a dimension greater than 1. Okay, then how the theorem looks like? So the theorem is like this. Let W be a subspace of Rn. Right, subspace of Rn means you will have some U1, U2, U3, etc. UP. All these are vectors which belongs to Rn. Okay, and the span, if you span this set of vectors U1, U2, U3, etc. UP, then you will get W. Okay, that is the subspace. It is known as the subspace of Rn. So let W be a subspace of Rn. That each y in Rn, I have A and arbitrary vector y which belongs to Rn, and each y in Rn can be written uniquely in the form of, or can be decomposed into two vectors. That is, one vector will be y cap and the other vector will be z, where y cap will be in w and z will be in w perpendicular. That is the what the subspace perpendicular to the w. That is w perpendicular. Okay, and in fact, if the set u1, u2, u3, etc., up is any orthogonal basis of w, that means orthogonal basis means this set u1, u2, u3 will be linearly independent, and also it forms if 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 you span this set u1, u2, etc., up, then you will get w. So that is what you call as orthogonal basis. So if it forms the orthogonal basis of w, then we will get y cap, right? Y cap, that means we have, for example, we have R3. Suppose now consider uh, okay, consider R3 three-dimensional space like this. Okay, and I have some vector like u1 and u1, u2, u3. Actually, this u1, u2, u3 are linearly independent and forms the orthogonal basis. So if you span u1, u2, and u3, if you span it, that means span of u1, u2, u3 will get a set of points you will get, and that set of points all you together constitute, then you will get a figure in three-dimensional space like this, or anything like this, where a three-dimensional space you will get. So that is what you mean by W. That is what you call it as W. So, and this is you can have a y cap. The theorem is saying that you can have a y cap, a vector y cap, so that this y cap can be generated. This y cap can be generated using these orthogonal basis vectors u1, u2, and u3. Right. So how you can generate? By using this formula which we have already discussed in the previous class. That is y cap will be equal to some linear combination of u1, c1, u1 plus c2, u2 plus etc. cp, up. Yes, where c1, c2, c3, etc. are y dot u1 divided by u1 dot u1, y dot up divided by up dot up. So these are the coefficients, right? So you can generate this y cap. This y cap will be a vector vector belongs to the subspace W, right? And then we have to find out the z vector. So what is z vector? Z vector will be perpendicular to the subspace W, or z vector is in W perpendicular. So the z is given as y vector y minus y cap, because we have y, right, and y cap we have find out using this formula number 2. So z can be find out. So you can decompose this vector or any arbitrary vector y which belongs to Rn into y cap plus z. So this is our theorem. Now, yes, this is our theorem, and you can have a geometrical interpretation of orthogonal projections, which will be very helpful in solving the problems also. Now, let me consider this figure. Okay, this is a three-dimensional figure, and it is having some like this. This is x1 axis, this is x2 axis, and this is x3 axis. Okay. Now I'm defining two vectors u1 and u2, two vectors which belongs to our R3, that is three-dimensional space. And this u1 is something like which is on a vector on x2 axis. So it will be like ordered triplet, uh, 0 x2 0, right? And similarly u2 will be like x1 from x1 0 0. So it will be our uh, i- in this way our vectors will look like, right? Right. Okay. So u1 u2 are the two vectors. Now I have an arbitrary vector y, which is something like a b, right? This is my arbitrary vector. Okay, arbitrary vector. Now, yes. Now I'm defining a subspace W, and this W is equal to span of u1 u2. Span of u1 u2. Span of u1 u2 means it will be the x1 x2 plane. W will be our x1 x2 plane, extending from minus infinity to plus infinity length. This will be our W, right? Span of u1 u2. W, that is x1 x2 plane. Okay, so by the theorem 8, what the theorem 8 says that this arbitrary vector y can be is equal to some y cap plus z. That means where this y cap will be in W and z will be perpendicular to the subspace W. Will be like this will be our z, which is along x3 axis, and our y cap will be yes. And this y cap is known as the orthogonal projection of y onto the subspace W. Right. Now this y cap, actually this y cap is what y cap is, if you consider not only y cap, if you consider some vector v, right? Vector v, an arbitrary vector, and it can be anywhere in W. Can be anywhere in W. Okay. Now, you join or you measure the length. You measure the length uh, L from the vector y onto each v. So you will get infinite number of vectors like this. Right. Now, if you uh, now the distance between you again measure the length between the y and y cap also, and if you compare all these lengths, the minimum length or the minimum distance will be the distance between y and y cap always. Okay, so in other words, you can say that y cap, which is the orthogonal projection, it can be defined as the closest uh, closest point in W, closest point in subspace W. Okay, W, which is or you can define like this: the point in the subspace W, which is closest to the vector y. Okay, that is what you mean by the orthogonal projection. So that is the geometric interpretation of orthogonal projection. Right. Now I have this y cap. I got this y cap. Now I am projecting this y cap again, okay, onto the vectors u1 and u2. onto the u1 and u2. Again I am projecting this vector. So what I will get? Y1 cap and a y2 cap I got. Okay. So then again I am applying this orthogonal decomposition theorem. So then what happens is that you can write this y cap equal to y1 cap plus y2 cap. Again, you can write like this. And this y1 cap and y2 cap is nothing but your orthogonal projection of y onto the u1 and u2. Onto u2 and u1 respectively. That means the that means the orthogonal projection of y onto the two lines, two straight lines passing through the origins which are perpendicular to each other. Okay. Then you add up those vectors. Okay. You sum that two vectors. Then you will get the orthogonal projection of y onto the subspace spanned by these two vectors u1 and u2. Okay, that is our understanding. Okay. Yes. Now, yes, properties of orthogonal projections. This is an important property that can be easily understood with the geometrical interpretation of orthogonal projections. Okay. Now, if u1, u2, etc., up is an orthogonal basis for w, right? Orthogonal basis for w. That means in this geometrical interpretation, I have considered u1 and u2 only. Okay, and u1 and u2 are linearly independent vectors which are which are orthogonal to each other. So and also it forms the basis for w, right? So this u1 and u2 can be called as the orthogonal basis for w. And similarly, in this the author is generalizing this. If u1 and u2 etc. up, if we have p number of vectors, such vectors, and these vectors are forms the orthogonal basis for w. Okay, and if y happens to be in w, that means y actually when we have discussed y is not in w, because w is x1 x2 plane, right? Y is positioned at somewhere in the 3D space. Okay, w is nothing but x1 x2 plane only. Okay, so y is not in w. Suppose y is in w. Okay, y is a vector in w. Let me consider like this. That means like this y will be some p, q, and 0. Why? Because elevation is not there. So z coordinate, x3 coordinate will be 0. So like this. If y is in w, then y happens to be in w, then the formula for projection of y onto w is exactly the same as the representation of y. That means in this special case, the y itself is the orthogonal projection of y onto the subspace w. If y, that means if the vector y happens to be in w, then y itself forms the orthogonal projection of y onto the subspace w. So that is our property. That means if y is in w, that's equal to span of u1, u2, etc. up, or in our example, which is span of u1, u2, and which is x1, x2 plane, then projection of y on w will be equal to y itself, because we have defined that the projection of y onto the subspace w is that point for which we will get the minimum distance between y and the minimum distance is for which we will get the minimum distance. That means the point in W which is closest to the vector y, right? That is the definition. So here the y is happened to be in W itself. So the elevation is 0. Okay, elevation is 0, and the closest point will be the vector itself. Okay. Okay. Now, yes, that is what the orthogonal projection property is. Now, theorem number 9, which is the approximation theorem. This theorem also comes from our discussion itself. That means yes. Let W be a subspace of Rn. Let Y be a vector in Rn, and let Y cap be the orthogonal projection of Y onto W. Then Y cap is the closest point in W to Y, in the sense that norm Y minus Y cap less than norm Y minus B. So that means we have discussed this just a little bit ago. Like we have taken a vector V, an arbitrary vector V, okay, which belongs to the x1 x2 plane, or W subspace, okay, W subspace, and the distance uh, norm y minus b means the distance between y and b. Norm y minus y cap means the distance between y and y cap. So the y cap will be in such a way that the orthogonal projection of y onto W will be such a way that the distance between y and y cap will be always minimum, always less than any other the distance between y to any other arbitrary vector v. Okay, okay, that is the theorem. Now going to the theorem number 10, that is yes, this theorem. All these theorem has got proof, but the proofs are not important to your exam. So this theorem number 10 is also you have to apply this theorem, and we will solve some problem. And if set u1 etc. is an orthonormal basis, they are saying, okay, orthonormal basis for a subspace W of Rn, then projection of y onto the subspace W will be equal to y dot u1 into u1. Why? Because orthonormal basis means u1 dot u1 will be equal to 1. New product will be equal to 1. So that is the peculiarity of orthonormal basis. Okay, orthogonal basis means u1 dot. Okay, u1 dot, actually u1 dot u1 is itself is will be, yes, u1 dot u1, and u1 dot u2 will be equal to 0 for orthogonal basis. Right. Yes, so that modification will be there here, so that y dot u, okay, so you will get this formula, and we are representing this u1, u2, u3, etc. up vectors as a matrix. In matrix form, you will get u into u transpose. That means inner product. This is nothing but your inner product y. Okay, that is what is the formula you have to always remember this formula, right? Okay, now we are going to the first example. That is, this example, the examiner is asking you to find out the y cap and z. Y cap equal to dash and z is equal to dash. That is, write y as the sum of a vector in W. A vector in W means that is nothing but y cap, and a vector orthogonal to W, that means z. So the solution will be like this. Because y cap orthogonal projection, we have the formula for this orthogonal projection of y onto W as like this. So you apply that formula, then we will get y cap. And also we have y equal to y cap plus z. So z will be equal to y minus y cap. So also you can find out z. So that y equal to y cap plus z can be verified. Okay, that's the solution. Now moving on to the next example. Yes. In this example, the examiner is asking in an indirect manner to find out the orthogonal projection of y onto W. That is indirectly he is asking to find out the closest point in W to y. That is nothing but the orthogonal projection of y onto W. So that is also very easy. Now going for the example 4, that is it is the examiner asking you to find out the distance from a point y in Rn to a subspace W, which is defined as the distance from y to the nearest point in W. So it is nothing but you find out the orthogonal projection y cap, okay, and then you find out the distance from y, that is distance between y and y cap. You find out that is nothing but norm y minus y cap, right? So that's it. Okay, that is given in the solution. I hope you understood all the discussions. If you have any doubt, you can clarify it. Okay, later. So thank you.